So I think we can start. Uh, or let's wait for a couple of minutes because people are joining. I can see. Okay. So meanwhile, please introduce yourselves. Uh, Pushkar, Rajendran sir. I think last day you had introduced Lokesh, Simon. So you guys are from BTech or hello sir.
Good afternoon, sir. I'm Kumaravil Rajendra.
Yeah, hi. Hello Rajendran.
Hello.
So yeah, can you please introduce yourself? Like you're from which background, or like are you doing BTech or from industry? Yeah, Rajendran sir. Hello. Okay, so I think we can start with the session. So good evening, everybody. I welcome you to the second live session for the course NPTEL course Oil Hydraulics and Pneumatics. The tutor for this particular course is Professor Somsekhar Seramat from the Department of Mechanical Engineering, IIT Madras. I am Arnab. I am the teaching assistant for this particular video, and I'm a PhD scholar at Department of Mechanical Engineering, IIT Madras. So I hope that you have gone through the lecture videos that have been published for week two as well as week one, because week one was basically the fundamentals, and week two we delved a little bit deeper into the factual parts like the symbols used in the fluid power industry. So today's session would be mostly concerning with those fluid power symbols and a few other basic numericals that I just formulated or collected uh, from the assignment and some other sources. Okay, so let's start. Sorry. Yeah. Okay, so I will expect that you guys you can answer through this chat, or you can also unmute yourselves and you can answer. Or if you're having any doubt, any query, you can pause me and ask the question. Okay, so coming to the first question, I hope that you're familiar with hydraulic jack, even if you haven't gone through the past week's video. Still, I think it's a common term. So, what is a hydraulic jack? Before going to its working principle and everything, let's understand what is a hydraulic jack. Anyone? What is the purpose? So, it is used to lift heavy loads, and it has a wide range of applications in different industrial sectors. So, we are taking the help of hydraulics to carry out this operation. And to be more specific, Pascal's law is the underlying phenomenon, or the underlying fundamental that we are using. So, roughly, you would have two interconnected cylinders which are connected through a hose, and you have a fluid medium here, and you will be applying a particular load F1 and the piston area would be say A1, and here you have a heavier load, say that is to be lifted, so that is nothing but F2, and the cross sectional area of the cylinder is A2. So as we understand from Pascal's law that the pressure in a fluid, it gets transmitted undiminished along the span of the fluid in case the fluid is at rest. So that is important. So essentially, the pressure that is acting at this point will be transmitted undiminished to this point. So you will get P1 is equal to P2. So pressure is nothing but force by area. F1 by A1 is equal to F2 by A2. And if you so this is basically the mechanical advantage. How much load you are able to lift by putting a particular effort. So F2 is the load, F1 is the effort. The mechanical advantage, it is nothing but A2 by A1. So since A2 is greater than A1, therefore F2 will be greater than F1. So by applying our mechanical advantage will be more than 1. Yeah. So this is just basic principle. I hope you're all acquainted with this. So the question asks, when the hydraulic jack is in equilibrium, the following statements hold good. Pressure is equal. So as we know that pressure on both sides will be same. So that is correct. Displaced volume is not equal. Displaced volume is equal. Work done in that is the input work is not equal to work done out, that is the output work. And the last statement is work done in is equal to work done out. So what is the work done? In work input is nothing but the force into distance, right? So F1 is the input force into the say this particular cylinder has 1 second. Okay, so say this particular cylinder has traveled by a distance of S1 while the load is being applied. And similarly, this particular cylinder has gone up by displacement S2. So S2 is the displacement of this particular piston or the load, you can say. So F1 into S1 is the work input, whereas work output is nothing but F2 into S2. So if we consider that there is no frictional losses, no frictional losses. So where would this friction come from? Friction would essentially come from since the fluid is flowing from this cylinder to this particular cylinder. So on the walls of the pipes there can be friction between the fluid as well as between the fluid and the wall of the pipe, as well as losses can occur due to viscous nature of the fluid. So viscous losses can also come into play. So neglecting those losses, we can write that W in is equal to W out. Since there is no other work that is being done on the system except W in, and also no other work is being dissipated or energy is being dissipated. So we can write this statement. So done is equal to work done out. So that is the E is correct. Now displacement. So displacement, as you can understand, is not equal. But what about the displaced volume? So from here we can simply write F1 S1 is equal to F2 S2. So from there F2 by F1 is equal to S1 by S2. Right. So one more thing, that is the displaced volume. So you should remember that the amount of liquid that is being, or the volume of liquid that is being displaced through this cylinder while the piston one is going down, the same volume of liquid has to be displaced up because this is a confined space, right? So you can understand that here the area of the piston, like it plays a major role because here the cross sectional area is low, so the displacement is high, whereas here the cross sectional area is high, so the displacement is low. So that balances out the volume of liquid. So displaced volume is equal. What is the displaced volume in case of one? It is nothing but area one into displacement 1. So area is nothing but mm cube, S1 is mm, is the displacement. So similarly, you can write area 2 into S2. Okay. So from here, again, area 2 by area 1 is S1 by S2. So all these expressions you need to remember in order to solve simple numericals that can be framed from this particular problem. Okay. So this was just the basic. Now I would like to ask that why is this particular thing equilibrium being mentioned? Why do we mention that when the hydraulic jack is in equilibrium, the following holds good? Anyone? What is the significance of this particular term here? So this is one of the assumptions that we had to, consider before proceeding into the problem. This is because this equilibrium essentially means the summation of external forces on the system is zero. So this is your static. We are dealing with static equilibrium or the liquid. You know, uh, there is no overall displacement of the liquid. So it is a hydrostatic problem. So we can say that whatever mm, wha- uh, like the velocity at which this particular piston is going down, that is uniform. There is no acceleration. Again, when the velocity of this particular piston, this output piston, that is also uniform. So there is no ma constraint. I hope you understand that the, this particular system is in equilibrium. So this is just the case of statics. I won't say that this holds, how will I express? Wait, 1 second. So I hope you understood. This would happen. Like if there is any inertial effect, then there needs to be an additional force that needs to be overcome, other than the weight of the body. So this inertial effect is not taken into consideration. So there is no acceleration of the system. So that's why we are saying that the system is in equilibrium. Okay. So let's come to the second question then. Venturi is used in which of the following engineering applications? So what is Venturi? Venturimeter, you have come across this term in fluid mechanics, also in hydraulics. So it is basically a tube with different cross sectional areas or different cross section. Generally, it is the shape of the cross section is circular. So what happens as the liquid moves? Now we are dealing with hydrodynamics, not hydrostatics, because here the entire liquid column is moving. Okay. So as the fluid is flowing from section 1 to section 2 to section 3, its properties will change along the flow. So, what are the properties that we are talking about? It's basically the pressure, or it can be the temperature, it can be the velocity, it can be the potential energy, and so on. So, these are the properties of the fluid. Now, if we make certain assumptions, as like there are no losses and the flow is steady flow, rotational flow, and the viscous nature of the fluid is also um, you know eliminated, or it's like considered to be negligible. In that case, we can write that the energy of the fluid possessed at section 1 is same as the energy of the fluid in section 2 and in section 3. That is the law of conservation of energy, right? So what are the components of those energy? That is what I am talking about. I hope you understand. That's Bernoulli's principle or Bernoulli's equation. So total energy at section 1, total energy of the fluid, I would say, at section 1 is same as that in section 2 and 3. So what are the components of the energy? One, you have the pressure energy, right? So if it is along a horizontal, plane, if this particular pipe is kept at along a horizontal plane, then Z1 is equal to Z2. So you can cancel this out. Now comes the pressure part. So another thing, if we are considering the flow tube uniform, then this rho one will be same as rho two, and let's consider that to be rho. Okay. So mm, from here you can write P1 minus P2 by rho g is equal to V2 square minus V1 square by 2g. Okay. Now, if you apply the continuity equation between section 1 and 2, then you have A1 V1 is equal to A2 V2. That is nothing but, like, I can also write rho 1 A1 V1 is equal to rho 2 A2 V2. That is nothing but the law of conservation of mass that is flowing across section 1 and section 2. And rho 1 is equal to rho 2. So I can cancel them out. So from here, A1 V1 is equal to A2 V2. So as we can understand, since A1 is greater than A2, so therefore V2 will be greater than V1. So that is basic intuition, because the fluid is trying to flow through a smaller cross section, so it needs to increase its velocity to maintain its discharge, right? So that's why the velocity of the fluid will increase, and hence we have this particular criterion. Now you see, since V2 is greater than V1, essentially that increase in velocity, this particular head needs to be compensated in the pressure part, pressure component of the energy. And so that's why this particular static head, it will reduce since the velocity is increasing. So since V1 is greater than V2, therefore P2 will be less than P1, and hence the pressure energy of the fluid, it reduces as it goes from here to here. Now, like that is the background of Venturi meter or Venturi. Now, where is it being used? In which of the engineering applications? Anyone? This decrease in pressure is the main USP here, and this is being applied. So, in engine carburetor, we are using this application. Once the pressure at this section falls below the pressure over this section, we keep a oil bath here. Not oil bath, sorry. It contains the fuel. Fuel will be injected to this section because the pressure at this section will be lower. P2 will be lower than P1, and the same pressure is maintained over the fuel tank also. So this is also P1 or the atmospheric pressure. Here also, at one you will have the atmospheric pressure. As a result, what happens since P2 is less than P1 due to this pressure differential, the fuel will be injected into the throat of the venturi. So this is used in engine carburetor. It is also used in flow meters in industrial pipelines, as we know. And if you join these two particular sections here and here, and if you are able to measure the difference in pressure between these two sections by using YouTube manometer and all, then easily you can calculate the flow rate through the pipe. That is another application. Coming to the next question. In a static liquid storage tank, the discharge velocity depends on which of the following factors. As you can understand, if the storage tank is static, which means that the liquid here is not moving. Like the condition of statics can be conveniently applied here. Suppose it was having an acceleration here, then the level would have been like this. The liquid level would have been like this. But in this case, the liquid is static. Okay. So the discharge velocity. So this is a storage tank, and here you have the discharge point, a tap or something. So if you open the tap, it will come out. The liquid will come out. So I'm just simply denoting it like this. If you apply Bernoulli's principle, Bernoulli's equation at a point just at the surface of the liquid, okay, and another point just at the point, just at the section at which the liquid is coming out. So at these 2 points, you can understand that this is exposed to the atmosphere, right? This is atmosphere. This is also atmosphere. So here, the pressure that is acting on this particular fluid section, that is atmospheric pressure. So you can write P1 is equal to P2 is equal to P atmosphere. Next, this particular section, if the water is draining out here at velocity, say V2, then sorry, then this is V2. Then at this section, say the water level is coming down at velocity V1, right? So you can write here that A1 V1, that is the rate at which the level of water is falling down, will be the same at rate or the discharge of the liquid through this bottom section. So A1 V1 is equal to A2 V2. Now, generally, you will find that the size of the tank is considerably much higher than this particular small orifice down here. So you can conveniently say that A1 is much larger than A2. Hence, V2 will be much larger than V1. So with this assumption, we can say that we can neglect the V1 component, right? And assuming that there are no other losses, so V1 by rho G plus V1 square by 2G plus Z1 is equal to V2 by rho G plus V2 square by 2G plus Z2. So Z1 is the potential head at of the liquid in section 1, and Z2 is the potential or the head at section 2. So Z2 minus Z1, or sorry, Z1 minus Z2 is nothing but the height of the liquid column here. So if this is your from the absolute zero, if this height is Z1 and this height is Z2, so the difference between them is nothing but H. And again, we know that P1 and P2 are equal, so we can cancel these two terms out. Next, V2 is much greater than V1, so we can conveniently, neglect this term V1. Okay, so what we are left out with is V2 is equal to root over of 2G Z1 minus Z2, which is nothing but root over of 2GH. So you can understand that the velocity at this section, or the discharge velocity, is dependent only on the height of the liquid column, or the on this particular column. It doesn't depend on the total volume of the tank. It doesn't depend on the shape of the tank. So it depends on the height of the liquid column, and there is another option: vapor pressure on the liquid. So what happens if you consider confined spaces, like if this particular end is confined and not open to atmosphere, then the pressure at this point won't be atmospheric pressure. It will be the vapor pressure of the liquid, that the pressure that the vapor has formed on the top of the liquid, that is being applied on the liquid surface. So at that time, P1 will be equal to the vapor pressure of the liquid, and P2 will be your atmospheric pressure. In case the tank is not open to atmosphere, if it is close to the atmosphere, then the vapor pressure will be the pressure at P1. So you can understand that P1 is may not be equal to P2. So another factor comes into picture, that is the vapor pressure of the liquid. So this is also correct. If again, like if the tank is open to the atmosphere, then the pressure that is acting on the surface of the liquid will be P1 or P atmosphere. This one. If it is not open to atmosphere, if it is a closed chamber, then the vapor pressure of the liquid will be coming into picture. So this is PVAP, which is nothing but P1 here. That time you can't cancel out P1, P2. So many other factors also come into play. The top of the tank, okay, we have a numerical here. The top of a water tank is open to air. See, here it has been mentioned, it is open to air. So, yeah, you can apply this particular equation. And its water level is maintained. So, again, which means that this particular H value is kept constant as the water is discharging out. How you may attach one inlet flow through here, like some liquid is coming up, and it is fulfilling the amount of liquid that is going out. So its water level is maintained, that is H is kept constant. It is giving out 0.74 meter cube water per minute through a circular opening of 2 centimeter radius on its wall. So you have Q, which is 0.74 meter cube, right, per minute. So you have to be careful about the units. It's not in seconds. And you have a circular opening 2 centimeter radius. So R is equal to 2 centimeter. Therefore, the area will be nothing but pi r square. Just help me with the values. I am not sitting with a calculator. So what will be the area? Pi into 20 square, right? Okay. So let's not you know let's keep it in meter because this one is given in meter cube. So 2 divided by 100 meter. So 2, the area is, this much say. So from here you will get the velocity since you would be knowing that q is equal to a into v. So here this a is nothing but a2. Okay. So I'm writing here a2 into v2, which is again a1, which will be again equal to a1 into v1. So from here v2 will be how much? So it's coming close to 9.81 meter per second. Please correct me if I am wrong. Are you also solving? Then please let me know what are the values that you are getting. 0.74 divided by pi r square, that is divided by 0.02 square. Yeah, I am getting 588.87 meter per minute. So just converting it to meter per second, you will get 9.814 meter per second. So that is V2. Now the question asks the depth of the center of the opening from the level of water. So a depth of the center of the opening from the level of water in the tank. So they are basically asking the value of H. If this is the opening, so this is the level of the opening and this is the level of water. So this is the depth that they are asking. That is nothing but your H. So we know that V2 is equal to root over of 2GH. So V2 square will be basically 2GH. So we will be having H is equal to V2 square by 2G. G is nothing but 9.81. So you can cancel that out. So V2 square divided by, it will be approximately 4.9 or 4.8 like that meter. Okay. Are you all getting this answer or are you getting something different? Please let me know. Okay, moving on to the next question. Well, this is also a numerical based on Bernoulli's principle, and it was asked in GATE 2018. See, like a direct question was asked. So these are scoring portions. All you need to be aware of are the units and what are the information that is being asked. Okay, so air flows at a rate of 1.5 meter cube per second through a horizontal pipe with a gradually reducing cross section as shown in the figure. The two cross sections of the pipe have diameters 40, 400 mm and 200 mm. Take the air density as 1.2 kg per meter cube and assume an inviscid incompressible flow. The change in pressure P2 minus P1 in kilopascals. So you have to note this between section 1 and 2. Generally, if they're asking this as a numerical answer type question, then you have to, like, you don't have any options in front of you, so you have to be careful about what units they're asking you to report the answer in. Okay, so again, this is section 1, this is section 2, this one, applying Bernoulli's theorem to section 1 and 2. So before that, you need to know the velocity at section 1, since it is given as in the form of discharge, that is q1. I am not writing q1 since it is maintained constant across the flow. So it is basically A1 cross V1. So from here you will get V1 is equal to Q by A1, which is 1.5 meter cube per second. That is SI only, divided by A1. So A1 here is, like, you have the diameters 400 mm. So zero point 0.4 meter. So pi into 0.4 square by 4. So this is diameter again, not radius. These small things you have to be careful about. The 400 mm is nothing but 0.4 meter. So zero point 0.4 square divided by 4. Okay. One thing, like, if you are comfortable converting these values immediately to simpler forms, then it is fine. Otherwise, you can keep it like this. In the final calculation, you can uh, like substitute the values. So that will save you some time. Every time you don't have to open the calculator window and all. 0.1 into 0.4. So what will be the unit of this? It will be meter per second, since this is in meter square and this is meter cube per second. So meter per second. Now you need to find the value of P2 minus P1. So P1 by rho g plus P1 square by 2g plus Z1 is equal to P2 by rho g plus P2 square by 2g plus Z2. Since it has been said that it is a horizontal pipe, so Z1 and Z2 will cancel out, and there are no losses already assumed. So P1 minus P2 by rho g is equal to V2 square minus V1 square by 2g. Again, V2 square you have to find out. Sorry, the value of V2 you have to find out, which is nothing but Q by A2. Right? So You're going to understand that by just doubling, you are reducing the cross sectional diameter by half, you are getting four times increase in velocity because V1 is inversely proportional to the cross sectional area, or you can say it is inversely proportional to the diameter. Okay. Okay. So from here you will get P1. Okay, so the question has asked you P2 minus P1. So these things you need to be careful about. So P2 minus P1, final pressure minus initial pressure will be rho into V1 square minus V2 square divided by 2. So rho I am considering as 1000 kg per meter cube because it's water. Oh, sorry. I am extremely sorry. It has been said that it is air, right? It has been said that air flows at a particular rate. So you need to consider the density of air, 1.293, right? What will be the answer? 11.937 square minus 47.746 square divided by 2 into 1.293. You will get approximately minus 1382 Pascal. So in kilopascals, it will be minus 1.382 kPa. So this minus sign is important because the question has asked P2 minus P1. If there is any calculation error, do let me know because I'm doing it on my mobile phone. Just let's go through it once. 400 mm square, so that's fine. 0.4 meter, 0.2 meter. I hope it is fine. Okay, now coming to the fluid power components. Okay, let's just recap on the initial part. Like in the last few questions, we came across different numericals where we applied the Bernoulli's theorem, Bernoulli's equation, and the Pascal's law. And this was Torricelli's theorem. So basically, it deals with hydrostatics and hydrodynamics. That is, the liquid is either at rest, the fluid is either at rest or it is moving. It is important in hydraulics and pneumatics because in hydraulic or pneumatic system, you have either air or oil that is moving through a pipe or different fluid power components. So later, when we will be solving numericals on design of pistons or motors, you will see that these things come into effect. Okay. Now coming to fluid power symbols. So identify the difference between these fluid power symbols. In one, you can see that what is this basically. So if you have a symbol that is going outwards from the element, then it is pump or motor. It is pump. If it is coming into the element, into the boundaries, then it is motor. Why? Because in pump we are discharging the liquid from say level 1 to level 2. So inside the system or the impeller of the pump, the liquid is, if we try to visualize the liquid, then it is flowing out. That's why this outward symbol. In case of motor, the energy is coming into the system. That's why this inward symbol. Anyway, these are just symbols. I'm just giving you some mnemonics. And if this is bold, so if this was like this, then it would have been pneumatic, or sorry, it would have been compressor, right? If it was like this, then it would have been pneumatic motor. So if this is bold sign or it is filled, then it is for hydraulics. If it is not, then it is for pneumatics. Now, pump can be of different types. It can be fixed displacement type, variable displacement type. Fixed displacement means that it can discharge only a fixed volume of liquid, no matter what. In variable discharge, it can discharge different volume of liquid based on the set parameters. So here, this particular arrow indicates that it is a variable type. That is, the this particular pump is variable displacement pump. So it is a variable displacement pump. And here you can see it is same, but there is this particular arrow. What does this arrow indicate? It indicates that it is having a pressure compensation. Pressure compensated variable displacement pump. What does this pressure compensation actually mean, and why is it required? Because we know that the pump is discharging liquid at a particular flow rate, say. So, in case there is some pressure that builds up in this pressure line, suppose either the load is, there is a heavy load that is not getting lifted, so there is a backflow of liquid, and the pressure in this particular line at the upstream line of the pump, the pressure gets built up. So in that case, there are chances that there is a leakage from the system, or the pipes can burst. There can be some catastrophic failures. So that's why there needs to be some sort of pressure compensation to protect the equipment or the hoses. So how is that done? There will be a system to read the pressure from this line. If that pressure is, say this is P2, if this P2 is exceeding a particular threshold value that is again adjustable, then what happens? The liquid is bypassed into the tank. If this condition arises, then there is a bypass system that will open up and allow the pressurized liquid to flow back into the tank. As a result, the pressure will be relieved. So this is called pressure compensation. There is another symbol for this, which is more elaborative. So this is the It leads from here. Okay. So this basically means that the threshold value of the pressure that is adjustable by the help of spring, and this means that pressure is being read from this upstream line. Okay, coming to the next question. Then the next, sub question. Yeah, what is the difference between these three symbols? Anyone? What is the difference between these three symbols? You can see that there is something different about the arrows in the three components. Okay, so this you can understand, right? There is a provision that the liquid can flow outwards or it can flow inwards, right? So this can behave both as a pump as well as a motor. And since it is bold, so that is for hydraulics, not pneumatics. And secondly, it is not a variable; it is fixed displacement. So fixed displacement pump or motor. And if you look at this one here, you can see that here the inlet or outlet can happen only through this particular side, whereas here it can happen through like two ends, but in one particular direction. So this is also a pump plus motor, which is fixed displacement, but fixed direction of flow of liquid. Here, in both directions, the liquid can flow. Okay, so I hope you understood. In the first one, the liquid can either flow in or flow out from this end. In the second case, the liquid has to flow in from this end and has to flow out from this end, not the other way around. Any other possibility is not there. While in the third case, liquid can flow in or out in case of pump or a motor from either ends. So if it is working like a bidirectional pump, so this is also known as bidirectional pump or motor. This is unidirectional since it is having one particular direction. So here you can understand if it was simply like this, then it was bidirectional motor. If it was like this, then it was bidirectional pump. So this is nothing but summation of these two, combination of these two. Okay. Okay. Coming to the third one, So here, what are these components? These are basically orifice or flow meter. So it meters the flow through the circuit. So this one you can understand it is a fixed displacement. Like here you can't vary the flow rate. Here a particular flow rate has to be maintained. Whereas here that flow rate can be varied because this arrow is being shown. But here another thing comes into picture, that is this particular non-returning valve. So what happens when the flow happens from this particular direction? Then it flows through the orifice. It can't flow through here because this NRV will no, it will not allow the flow to happen from this line. Whereas if the liquid is coming from the fluid is coming from this direction, then what happens? Here this ball opens up and it allows the liquid to flow here. And since this is causing a resistance and this is the least resistance path, so the backflow won't be metered. So this is only meter in flow. Meter like it is like the outflow is not metered. Sorry, yeah, the backflow is not metered. And here again, this arrow indicates there is a pressure compensation. So based on the pressure, this flow will be regulated. Hello, am I audible? I think I just logged out mistakenly. Just give me 1 second. There is a problem with the recording. Okay. Identify the following types of actuator and find the odd one out. So you can see that there are four actuators here. So this is a double acting cylinder, simple double acting cylinder. Why double acting? Because as the liquid is flowing in through one side, the liquid on the other side will flow out. In this case, this is also double acting cylinder with cushion, this particular cushion. So again, liquid can flow in through here and flow out through here. While the piston is returning back, at a it won't touch the um, end of the cylinder. Rather, it will be cushioned by this particular thing. And this is present only on one end of the piston. In this case, again double acting cylinder, but the cushion is provided on both sides. So at both the extreme ends, either here or here, that cushioning will be effective. Now coming to this one. This one is a telescopic cylinder, but it is a single acting type. So as the liquid is flowing in here, first it will fill up this particular volume. Next it will fill up this volume. So this cylinder will get extended. Next it will fill up the smaller cylinder. Then that will get extended. So that's why we call it telescopic cylinder. So three concentric cylinders, they will be activated sequentially, and you will get a larger, length. This type of actuators you might have seen in cranes, where they try to, you know, in long, utility cranes where suppose they want to keep something at a larger height, so from the ground. In that case, they have telescopic system here. So normal retracted position, it will look like this, and at extended position, it will look like this. Okay, draw the symbols of air compressor and vacuum pump. This is air compressor. What about vacuum pump? Acha, so here, which one was the odd one out? This is the odd one out because it is a single acting cylinder. Liquid is flowing in from one direction, and for retraction purpose, it will flow out from this particular line only. There is no separate line for the liquid to flow out, right? So, yeah, tell me this one. What would be the difference in the symbol for a valve? Sorry, vacuum pump. Anyone? Anyone? Like, what will be the difference? So vacuum pump means here also the flow would be in the outward direction, but there has to be a suction in that particular direction. So this suction is external to what the you know it is external to this particular system. Like in case of air compressor, you have a rotor which is rotating, and accordingly, like it sucks in air at a particular pressure, and it compresses it and pushes it out at a particular pressure that is higher than the inlet pressure. But here, what happens? The suction is created externally, and it will take in the liquid, right? Sorry, not liquid. No. Name the following components. So, what are these components? Anyone? Anyone? Like, what is this? This is the simplest one. So, if you have one line from here, it indicates it is a lubricator. Essentially, lubricator means it is a pneumatic component because in hydraulic you don't need external lubrication. So, it is obviously a pneumatic lubricator. And the other ones, this is a filter. By this perforated symbol, you can understand it is a filter. But this small triangle here, it indicates it is automatic drain. So in filter, there will be some dirt or liquid that is accumulating at the down what section that needs to be drained out. So that can take place either automatically or manually. So this symbol means it is automatically drained out. This is also a filter. And what is the difference between this filter and this filter? What is the difference between this and this filter? Anyone? Like what? These symbols have been discussed, right, in the um, lectures. So you should be able to answer this. So this one is basically a, like this is also a filter, air filter or pneumatic filter with this particular component is a contamination indicator. Okay. And coming to this one, what is this? Is this a filter? It is also a filter, right? Because you have this perforation. But there are two special things with it. First of all, this is a pressure filter. Generally, it's used in hydraulic line. It may be used in pneumatic line, but generally it is used in hydraulic line. And this downward arrow, it indicates that it is a line filter, a pressure filter or line filter with this particular bypass system. What is the work of this bypass? So it means that if the flow is happening in this from B to A in this particular direction, then it can't flow through this NRV or non like sorry, it can't flow through this through this valve because it will block the flow. But when the flow is happening from A to B, so in that case from B to A, it needs to flow through the filter, right? So at A you will be getting filtered liquid or filtered fluid. But when it is flowing in the opposite direction, from A to B, it need not line. It will come directly through this particular valve. It will open up at a particular threshold pressure of the liquid. It will open up and allow the flow to happen in this direction. So in that case, it won't flow through the filter. Okay. So identify this particular fluid power component and draw the symbol. So we discussed this in the previous session also. This is nothing but a filter, regulator, lubricator unit. So this is the middle part, that is the regulator. This is your, sorry, this is your regulator, this is your lubricator, and this is your filter. F, this is R, this is L. Okay. What are the symbols of FRL? Symbol of FRL. It is very important because in pneumatic systems, once the air is being treated, you have to, like, once the air is being compressed, it needs to go through a FRL unit so that you get rid of dirt, you get rid of different contaminant particles, and also at the same time, a small amount of lubricating oil is being spread or emulsified into the airstream. So that allows uh, better frictional performance in the sliding paths like the pneumatic cylinders and all. So what is the symbol for this? It is very simple. You have a filtration unit, so that perforated line, regulator unit. So this is the symbol of regulator, and this is the lubricator. So a small line from the top, that is the symbol of lubricator, as I mentioned here. Next, identify the difference between this and this. First of all, what is this? This is basically a non-return valve, right? But you can understand that there is a catch with these particular lines. So any dotted line would represent a pilot line. That is, to activate this particular NRV, you are taking a signal from somewhere else in the circuit. So it can be basically a hydraulic or pneumatic symbol also. That is, a pneumatic or hydraulic flow at a particular pressure or flow rate will activate this valve. So so that is basically called pilot line. Now, in one case, you can see that it is present before the NRV. In one case, it is after the NRV. So essentially, if the flow is happening, taking place in this direction, then this particular line, it is called like this particular signal will be used to check the flow in, you know, this is basically called pilot to open check valve or NRV. And this particular, if it is on the outer output line, then it is called as the pilot to close check valve. Okay, so these both of these are NRV. So this is pilot to open, like NRV is also known as check valve. So now this is pilot to open check valve, and this is pilot to close check valve. Okay, by the symbol. This is also known as shuttle valve or double check valve. How does it work? There will be flow from both X and Y direction. So the side from where the pressure is higher, that side the ball will slide. From that side, the ball will slide to the other side where the pressure is lower, and hence flow will be dominating from that particular end. So what I'm trying to say is, suppose the pressure at the X side is Px, pressure at Y side is Py. Then if Px is greater than Py, the ball will be shifted to this particular region, and the dominating flow will happen from the X side. Okay, generally one side is kept closed and the other side is kept open. So suppose X, Px, Py is 0 and Px has a finite value, say 5 bar. Then what happens? This ball will slide to here and rest here, and the flow will, at A, the flow will be received from X. This is how the cross section basically looks like. Very simple, but very essential, because this fitting should be a very close fit. Like, you can't keep much tolerance here, and dimensional tolerance is very low, and it should closely fit to the tolerances. because if there is little bit inaccuracy or mismatch, the liquid will leak out, and the valve won't be working as desired. One particular application here you can see that, suppose when you push this particular valve, sorry, this particular direction control valve, then you want the cylinder to extend. If you push this particular valve, then you want the cylinder to retract. So these are basically direction control valves, and this is your shuttle valve. So how it takes place, as you are pressing this, then the pressure line will be here. It will go through here. Whereas this is connected to the tank line, return line on the tank line. So what happens here? Px is finite value, some finite value at which the liquid is flowing, and Py will be zero. So this ball will be shifting to this side. Now the liquid will flow into the cylinder, and the cylinder will extend. During the return stroke, what happens? You are pressing this, so this will be the configuration now. So the liquid will be flowing from this side to here, and since this has a spring loaded onto it, you have to, as you let this particular thing go, this particular push button go, then this configuration will be retained. This configuration of the valve will be retained. So now the flow is happening from here, and the valve will be pushed here. Since this is the return line, and it allows the liquid to flow like this. So sorry, this is not helping in retraction. Rather this helps the flow to happen from this particular side. Okay, from this particular side of the cylinder. Suppose you want the retraction to happen at different speeds, so that is governed by the pressure at which it is the liquid is being pumped. So suppose this pressure is Px and this pressure is Py. Depending on the value of Px and Py, the speed of uh, this extension will vary. It can be Vx or it can be Vy. So if the flow is happening from here, then it will be Vx. If the flow is happening from here, it will be Vy. This is just a typical application. There are many other applications that we will come across in subsequent classes. Okay, so these are part of manual spool actuation. So what is a spool? In a direction control valve, here itself, so in this direction control valve, you have a spool inside the valve that is being actuated by an external mechanism. So that mechanism can be electrical, it can be mechanical, it can be manual. So the question asks, these are like which of these are part of manual spool actuation? Anyone? Manual means a person needs to manually handle that. Some of the manual spool actuation, anyone can tell me? I call and tell. Like you can have button type. So this one is manual actuation type because this is a mushroom button, right? So this is correct, and this one also. Since this is a pedal type manual spool actuation, this is mushroom button type. What about the other three? What about this one? So these two are the correct answers, but I'm just asking what does these other three indicating? This is a solenoid valve, solenoid actuation. This is a solenoid actuation, and it is having a single winding, right? And what about this one? This is a mechanically actuated valve and is also known as roller actuator. So this is used in cases of cascading cylinder. Suppose one cylinder is actuating the operation of another cylinder. Okay, so in that case, what do we do? Suppose this is one of the cylinders. So, and you have a direction control valve here. Say, so what will happen when this roller, suppose, will go and sorry, this particular cylinder will go and hit this roller. This is kept. This particular valve is kept at the extreme position of this cylinder, at the extended position of this cylinder that was here. So when the cylinder will go and hit this position, it will slide over this roller. Then what happens? It is denoted by this basically, like this. So then what happens? It will activate the flow from here. Okay. So okay, I'm just showing it in a better way. Suppose you have a double acting cylinder and a direction control valve. Okay. Originally say when it is not actuated, just I am showing one example. The liquid will flow from here to here and it will extend the cylinder. Now, as the cylinder comes to this particular position, say A naught, this is also the position A naught, it will activate this particular direction control valve. Okay. Then what happens? The flow will be coming like this configuration will be then activated. Now what happens? The flow happens from here into the tank through here. So this is just a very simple example. Actually, it is used in cascading cylinders. I just showed using one cylinder, but it is generally used one cylinder is activating the operation of another cylinder. In that case, this type of actuation is used. And what about this one? What is this? What is this? This is a cam rod type actuation, mechanical actuation.
Plunger type.
Ah, yes.
Plunger type.
Actually, it is not plunger. Plunger it generally it looks like this, but it looks like cam. It is a cam rod type. Like you have a cam and you have a follower. So if this cam rotates, this particular follower will activate the switch and it will actuate. Okay. So which of these fluid power symbols are used for accumulators? So this is basically what an accumulator looks like. It accumulates a particular volume of liquid, accommodates a particular volume of liquid. So these are the three symbols which we show in case of accumulator. What are the difference? This is a spring-loaded accumulator. Okay, this is normal accumulator. Like you are putting it along the flow, so this will get filled up, and after that it will flow through here. So it helps in causing a delay in the particular fluid power circuit. Suppose you want to activate a particular valve after a certain amount of time. Like I can give you one example. Um, Say you want to clamp this job, So you have a clamp which is activated, which is hydraulically realized. So this clamp will hold onto the workpiece, and after that, milling or drilling machine will come and make a hole through this. Okay. So you want that after this clamping has taken place, I want say 2 seconds of delay, and then the um, second operation will start. So then this hydraulic motor will come and drill a hole. So in that case, you need to put an accumulator in the circuit so that that time delay is being realized. What about this one? This had an external, sorry, it is a loaded accumulator, some you know weight loaded pre-pressurized accumulator. This we already discussed. It is an automated drainage type filter. Coming to the final question, illustrate the different center or neutral positions of a 4 by 3 direction control valve with their salient features. So, what is what does this 4 and 3 actually denote? When we say it is a 4 by 3 direction control valve, what does this number 4 and number 3 actually denote? This 4 is
Four,
basically the yeah, someone
yeah,
telling.
4 ports, 3 positions, sir. The number of ports,
Yes, yes,
4 ports, 3 positions.
yes, correct. So number of ports means the port basically means from where the liquid will be coming into the valve or going out of the valve, and position means the combination of the operation of these ports. From which port or which of the ports liquid will come in or go out. So how many combinations are possible for that particular valve? That is the number of position. So 4 by 3 DCV basically means 4 ports. So three, I am drawing a box. So there will be three sections to denote the three positions, and there will be 4 ports. Out of these three positions, the central position is called the neutral position, and the other two positions are activated positions. So they are activated either by spring, or it uh, can be activated by manually or through some solenoid valve. So that depends, like what type of actuation we already discussed in the previous question. So always remember this is the neutral position, that when you're not activating it through any external mechanism, this position will be held in the circuit. So what are the 4 ports that we are talking about here? One will be your pressure. Sorry. One will be your pressure port. Okay. Pressure means that pressurized liquid will be flowing in from that port. Another will be your tank port, which means the oil which is recirculated back into the tank will flow out through that port. Other two ports are for the cylinders or the uh, you know uh, suppose you have a cylinder like this double acting cylinder, then they will be connected to the cylinder. So port A and port B are the cylinder ports. Generally, this denotion is done at the neutral position. That is, like instead of sorry, instead of denoting here, people would denote in this position P, T, A, and B. Now, suppose this is one of the activated position. This is the other activated position. That is, the pressure port is connected to A in this case. Here, the pressure port is connected to B, and the um, tank port is connected to A. So that is for the reversal of the action of a particular cylinder. Now, this neutral position can be of different types. One, it can be closed type. This is called closed neutral. So, as you can understand, if the pump is pumping in liquid or the hydraulic liquid through here, it will pressurize the system because uh, this liquid is getting stored in this line. There is no place for the liquid to drain out. Okay, so that is not desired. This closed neutral is generally not preferred. There are other neutral positions like, so I'm just drawing the central position now onwards. So there is another neutral position that is called open center. Open center means like this. This is your PT, this is your AB. Okay. So what this means, this is open, central, center or neutral. Okay. This is your closed neutral or center. This means that if this is your pump, at the neutral position, the liquid will flow from the pump to the tank. It will not get held up in this particular line, like in this case. So this is one outcome. But here you can see that from like liquid can flow either from A to B or B to A, right? So if you want to hold a particular position in you want to hold the cylinder in this particular position, then that may not be a desirable choice because the load can allow the liquid to flow out of A, right? And that can flow into the tank. So this open center is not applicable for higher load applications where the cylinder can automatically get retracted by the action of the dead load. Next is your what other centers are available? You have a tandem center. This is the tandem center. Here you can see that if you want to lock the position of the cylinder, then this is possible here because even when you are even when you have not activated this particular direction control valve, the motor will continuously pump and that will go into the tank. So this recirculation will take place whereas the these two ports are closed. So that position will be held, tandem center. Next, so this is the float center. I'm see this is not this pump is actually not a part of the direction control valve. Just for illustration purpose, I'm showing it. So here you can understand that suppose this is your cylinder. So if a greater pressure builds up here, then automatically it will drain out through B into the tank. Okay. There is another center, that is this one. So this is also known as the regenerative center. Here what happens, you can see that, see, if you are keeping the pump on, first of all, while you are operating in a hydraulic circuit, you want to say direct a flow from one line to another line to operate one cylinder and then next another cylinder. In that case, you can't switch on or switch off the pump uh, frequently. You have to use the direction control valves to maneuver the flow across the circuit. So in that case, in this types of in this type of operations, although you are preventing the pressure buildup in this line, but still you see that the energy of the pump is going waste because it is simply pumping the liquid back to from the tank back to the tank. That is not desirable, right? So what happens in case of regenerative center? Suppose, so here you can see that the P line is connected to both A and B. So suppose if there is a larger load at B side, okay, because it can so happen like your cylinder is acting against a higher load, or you want to retain that position of the load, uh, retain that position of the cylinder against a dead load. So in that cases, what happens? Pressure at B side will be higher. So that will try to push the liquid A, push the liquid through A. Now, since the pump is on here, it will not allow the liquid to come back in this line. It will force it to go towards the B side. Okay, like this, it will go. So what will so yeah so what will happen? Like this particular flow will be um, countered by the flow of the pump. So as a result, like there will be a regenerative action taking place. So this regenerative action is why we name it as a regenerative center. Okay, I would suggest that you go through this particular section, like which center is used in um, which scenario from any standard textbook. I tried to explain it from my end, but there are certain intricacies like where this is used and where this is not used. So one factor is like you need to hold the load at a given position, hold the position of the cylinder at a given instant of time against a load, against an acting load. Second is you need to prevent buildup of pressure in the reduce wastage of energy. That is, your pump shouldn't be again redirecting the flow back to the tank. So, based on these criteria, you will choose, and your applications obviously, you will have to choose either closed neutral center, that is this one, all the ports are closed, there is no flow, but there is buildup of pressure, or open center, wherein all the ports are open to each other. So the flow can easily happen from P to T, or here you can understand that pressure at the A side and the B side will be uh, equal, because this pump will be flowing and compensating the flow, compensating that. Here it is the tandem center where A and B is locked at a particular position, but the pump is kept on. So this reduction in energy wastage, that is not fulfilled here, that criteria. In this criteria, you can understand it is a float center where this position is floating, right? Like if pressure builds up on one side, it won't be, you know, it won't be stable. It will try to retract. Next is this regenerative center. This regenerative center is actually interesting because here you can hold the load. There is, and you are using the pump pressure to hold it actually. So that's why we call it regenerative. We will discuss one numerical on this regenerative type center, like what happens actually, what happens to the flow in the next session. So it will be much more clear. You just go through this one, like what are the features of this different type of centers. So if you are having any other doubts, you can let me know. Yes, so let me know if you are having any doubts. You're not having any doubts. Yeah, anyone, any doubt? Or shall we wind up the session then? If you're not having any doubt, then we can wind up the session. Someone unmuted, I think.
Sir, I have one small doubt. In this flow controls, this flow divider is something different, or it is same as this one orifice mill control, sir? Flow divider in this flow control.
This one, you. Acha, flow divider. Okay, okay,
Ah,
okay.
sir.
Flow divider is basically like it will divide the flow into two or more than two sections of the circuit. Suppose you are discharging 5 meter cube per second, or like I'm just giving a rough value. It can be less than that. Suppose 5 meter cube is taking place. Now that is to be divided into three sections of the circuit. In one section, which while you are running one equipment, you need 2 meter cube per second. In another system, you need 2 meter cube per second. In another system, you need 1 meter cube per second. So accordingly, the flow needs to be divided based on the capacity of each system. So that is where the flow divider comes into picture. It controls the flow. So obviously, it is a flow control valve. So I hope you know the symbol for it, right?
Yeah, understood. But suppose if I
Ah.
require equal flow in all the two or three, whatever the flow divide is there, that is possible, sir.
Hmm.
Yeah, because I have faced some problem in one of the hydraulic presses where we have two cylinders and each getting different flow. Then we introduce a flow divider, but still
Yeah,
I have not.
like
Yeah,
see, flow dividers can be of different, types. So there, obviously, there are standard proportions. You do have 50%, 55, like 1:1, flow divider, where the suppose Q discharge is taking is going in from here, Q/2 from both sides. So if you are having say two hydraulic presses, one is running at Q/2, other is also running at Q/2, then you are using this type of flow dividers.
okay. But during that flow discharge, any pressure variation will happen, sir.
Pressure variations may happen depending on the load on each of these circuits. Suppose on this type, see, this is basically bifurcating the flow. Now, the
Okay,
pressure buildup is based on the resistance. Suppose one of the hydraulic cylinders is operating at a particular pressure. So, and at that same time, the other cylinder is not operating. So, the pump is discharging Q/2 into both the circuits, right? But in
correct.
one circuit, you are having a backflow, like you are having a back pressure. So
Load is acting on.
the flow is happening against the pressure. So in that circuit, there may be buildup of pressure. In the other circuit, the pressure won't be built up because the resistance is not there, right?
Not right,
But
right.
your flow divider will maintain the flow in both in both
Okay.
in both circuits, basically in this circuit also, in this circuit. Now, suppose you are designing a shop where you have two or three hydraulic presses of different capacities. One is running at a higher discharge, another is running at lower discharge. In that case, you are choosing the flow divider, say 50, 30, 20, like that. Depends on your application, 40, 40, 10.
Yeah, thank you, sir.
Hmm. Okay. Anyone else? Any other doubts? Okay, I haven't written down the names, I think, for these elements. Can you tell me the name of this particular elements? These are all flow control valves, right?
I think first one is a free flow orifice, sir. Free flow.
No, it is not a free flow. It is a fixed orifice, right?
Fixed
Only a
orifice.
fixed. Uh,
Second was is unidirectional adjustable check valve.
yeah,
Unidirectional
yeah, right, right. Adjustable means generally we write variable,
variable.
variable orifice with
Uniflow
a particular direction. Yeah. So with you can say um,
with the check valve, sir.
mhm, check valve. So what it does it if we are allowing the flow from this direction, then it is a metering flow that flows through this orifice. But when the flow is happening in the opposite direction, then it can flow through. Sorry, sorry, it can flow through this line because this is the least resistance part. What about this one? So you have this arrow here. What does that indicate? This is also a variable orifice, right? But you have a pressure compensation. This particular arrow represents a pressure compensation. Okay. This I think you understood. This is like it acts like a fixed capacity. So if you try to write the full name, it will be somewhat like uh, I just segregated it and told now. So it can be like a fixed capacity. If there was an arrow, it would have been variable capacity. Pump or motor with reversal of flow direction. Okay. This will be fixed capacity pump or motor with unidirectional flow. This will be fixed capacity pump or motor with bidirectional flow. So you can expect this type of questions in the final exam, where you will be asked to identify a particular hydraulic component, or you can be asked to draw the symbol for a given component. Okay, then I think that's it for today's class. If you have any other doubts, you can obviously write in the NPTEL portal. We will address them, and we will encourage that you attempt the assignments sincerely, and they will be helpful for the exams. How many of you are planning to write the exam for this particular course? Because last few years I have seen that many people are writing exams. Close to 200 or even more than 200 people take the exam for this particular course. You're also encouraged to take the exam, so that you know you are learning something, how well you are able to understand the things and apply uh, in actual applications that can be tested in those exams. So okay, thank you. We will meet again next Saturday, 6 to 8 p.m. You're closing.
Yes, yes, thank you, sir.
Yes, please. You have anything to ask, sir?
Sir, the same link will be used, no, sir? Same link next week.
Yeah, yeah, yeah. Same link, same link. The link will be same.
Okay. Thank you, sir.
Hmm.